This video is for lesson 9-3, reflections. Learning goals are to perform reflections on a coordinate plane and without a coordinate plane, and to identify reflectional symmetry in flat figures. Mr. Scott plans another transformation for that marching band. The sign of the y-coordinate of each marcher changes from positive to negative. Maria, whose position is shown by the x, moves from point 2, 4 to point 2, -4. So here we see Maria's position within that rectangular arrangement of the band members here at 2, 4. That's where she's always been located in each of these lessons. And then following this transformation, she ends up here at 2, -4. If her band mates follow in turn, the entire rectangle will have shifted to this position on the football field. This type of transformation is called a reflection. Reflections are sometimes called flips because the figure is flipped like a pancake. On the coordinate plane, examples of reflections are defined by functions that look like this. X, y goes to -x, y, or another example would be that x, y goes to x, -y, where it's the y-coordinate that's reflecting. Or another example is x, y goes to y, x, in which you are reversing the x and y coordinates. That would define a reflection across the diagonal line y equals x. Every reflection has a line of reflection, which is the line that the reflection maps to itself. In the above diagram, the line of reflection is the x-axis. Think of it like this. We have this original rectangle filled with band members. Here's the x-axis. I'm drawing it in brown. And then that rectangle is reflected over the x-axis and ends up here. So the x-axis in that case is called the line of reflection. It creates a vertical flip of a figure. Number 1, complete the table for the two reflections. So here we have some members of the band located at these ordered pairs. Where do they move to after the transformations? The first one we're going to do here is to use this formula. X, y goes to x, -y. Keep the x value the same, take the opposite of the y value. So 1, 10 would transform into 1, -10. 6, 10 would transform into 6, -10, and so on. Another transformation might look like this. X, y goes to -x, y. Switch the x value, but keep the same y value. And so 1, 10 would transform into -1, 10, and so on in the table. The figure shows an arrow drawn in the coordinate plane. The tip of the arrow is located at 4, 10. Here it is in purple. That's 4, 10. Number 2, predict the direction of that arrow after these reflections. If you reflected it across the x-axis, so let me trace the x-axis in brown. If you took that figure, which looks like an arrow, and you reflect it to the other side of the x-axis, what would it look like? Well, I think it would be pointed down. Question B, if we reflect that across the y-axis, I think that arrow would point upwards. Here's the y-axis, and if we take that and we flip it to the other side and draw it, it's still going to point upwards. Number 3, draw the two reflections. Were your predictions correct? And so here are my drawings of those reflections, taking that original arrow and reflecting it to the other side of the x-axis, and indeed it goes downwards. Question B, taking the original arrow that was in purple, reflecting it to the other side of the y-axis, and it looks the same as the original purple arrow. Number 4, what reflection maps the arrow to a downward arrow that also has the tip at the point 4, 10? So let me go back to the original picture. We want to have the tip of the arrow stay right there at 4, 10, but we want the arrow to point downward. We would need it to end up kind of like this. So how could we flip that so it looks like this? What if we flipped it over this line that I'm drawing across the screen right now? That's the line y equals 10. It's a horizontal line crossing the y-axis at 10. And so that is the answer to that question. We would need to reflect it over the line y equals 10. Number 5, could a reflection map the arrow so it points to the right or to the left? And the answer is yes. If the line of reflection is y equals x, then the transformation would look like this. Imagine that this purple arrow is that original arrow that was drawn above, and this diagonal line running with a slope of +1 upwards like this is the line y equals x. If you reflect the purple line to the other side of that diagonal line, it would look like the green arrow, and that points to the right. If the line of reflection is y equals -x, then we would have this situation. So again, here's the original arrow, the one in purple. The line y equals -x has a slope of -1. It runs downhill, goes through the origin. If we were to reflect the purple arrow to the other side of that line, it would be this green arrow, and that points to the left. Mr. Scott arranges the tuba players in an arrow formation shown below. Then the tuba players undergo a reflection that is described by the function x comma y goes to 8 minus x comma y. So I notice that the y coordinates are going to stay the same, so the tuba players are going to stay in the same level, right? They're going to have the same y value, but the x coordinate of their location will change using this formula 8 subtract x. So what I've done here is I've looked at the tuba players that are standing at the corners of the arrow shape. There certainly could be more tuba players within that shape, but I'm going to pay attention to the corners. This guy right here, the green dot, is at 0, maybe 5.5. According to this formula, to find his new location, we go 8 subtract x and then keep the same y value. So we're going to keep the same height of 5.5, but to find the x coordinate, we're going to go 8 subtract 0, which is 8. And so you see the other green dot? That's where that person moves to. He's now going to be located at 8, 5.5. I've done that for every dot that you see. So let's look at the red dot. The red dot has an x coordinate of 2, and then it's at that same height, 5.5. So I went 8 subtract 2, which makes 6, and I kept the y at 5.5. And so this red dot is where that person moves to. I've done that for every person, and I've color-coded it so you could keep track of which person moves where. There's one person that doesn't move. That's this guy right here. He's not going to move because his x-coordinate is 4, and when you plug in 4 into that formula, you get 8 minus 4, which is still 4. So he stays in place, but all the other tuba players move. When you draw in the shape that's created, it would look like this. Notice that that's a reflection. So number 6, draw the reflection. There it is in brown. And identify the line of reflection. For the original arrow that was drawn in black ink to end up looking like the one in brown, we have to have reflected it over this vertical line right here. And this is the line x equals 4. It's a vertical line crossing the x-axis at 4. Number 7, which tuba players travel the longest distance during the reflection and identify the distance? Well, the guys that had to walk the farthest were the ones over here. The guy who is the green dot and the guy who is the brown dot. And if there was any other tuba players standing right in between them along the y-axis, they would walk the farthest to get way over here to create this part of the new arrow. And so my answer is the players along the y-axis move 8 yards to the right. They're moving from here all the way over to there. That's 8 yards to the right. Number 8, which tuba player does not travel any distance at all? And that was the dude at the point of the arrow. He stays at 4,5. Number 9, explain why the reflection does not change the distance between any given tuba player and the point 4,5. Well, a reflection is a rigid motion, and rigid motions preserve size and shape. Another way to say that, of course, is they preserve the distance between points. So we just looked at reflections on a coordinate plane where you're working with x and y coordinates. Let's talk about reflections that aren't drawn on a coordinate plane. So like other transformations, reflections can be defined independently of the coordinate plane. A reflection is a transformation that maps point P to P prime. We had talked about how to speak this in the other lesson, across line L such that these two things are true. If point P is not on the line of reflection, then that line is the perpendicular bisector of segment PP prime. If point P is on the line of reflection, then point P is equal to P prime. Think of that as the case of that tuba player on the tip of the arrow, the guy that didn't move at all. His original location was equal to the image of that location. To describe reflections, we will use this notation. There's going to be a lowercase r for reflection, and then a subscript will be whatever the line of reflection is. In this case, a cursive L, so line L. And then right here, this is the pre-image, the thing that's being reflected, and then that will equal to, and then this will be the image. So what this is saying is if we reflect point P over line L, that will map to, or that will go to, P prime. Number 13, the diagram shows pentagon ABCDE and the reflection using those symbols, meaning reflect over line L. Question A, where would line L have to be? In order for this pentagon on the right to be the reflection of this one, where does line L have to be? Does it make sense that it has to be a vertical line that's perfectly in the middle between those two figures? That would be the line of reflection, line L, where you have to have equal space from there to there, as what it is from there to there, that these have to be equal space. Question B, label the point labeling A prime, that the reflection of point B we're labeling B prime. So, of these corners, which one's A prime? Well, it's going to be this one. Which one's B prime? Well, look how close B is to the line of reflection. So when you move an equal amount to the other side, that's B prime. This is C prime. This is D prime. And that one's E prime. Number 14, quadrilateral ABDC was constructed by drawing scalene triangle ABC. Okay, so here is triangle ABC. I'm going to highlight it in brown. Imagine that this triangle existed first, and that what happened was it was reflected across line BC. So here's line BC. If we reflect the brown triangle across the line, it would end up landing here. And that's where the quadrilateral came from. Point P is the intersection of segment BC and AD. So where this crosses the one going across, there's a dot there, and that's where P is. Question A, prove that segment BC, this one, is perpendicular to AD, which is this one. We want to prove that this is a 90-degree angle. Here's how the proof goes. The reflection of point A over line BC is point D. What we're saying is that point D is the reflection of point A. And therefore, by the definition of reflection, AD is perpendicular to BC. Where I'm getting that from is this definition from earlier, this part right here, the first dot of the part. If the point is not on the line of reflection, and point A was not on the line of reflection, then that line is the perpendicular bisector of this. Question B, explain why length AB, so this one right here, that segment, is equal to length BD, this one right here. Why are those things equal? Well, the reasoning goes something like this. The reflection of point A over line BC is point D, right? The same thing we had said before. So because this point is the reflection of that point, and because reflections preserve distances, then we know that this distance must be equal to this distance. That item we just did is related to the perpendicular bisector theorem. This theorem states that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And the converse is also true. If a point is equidistant from 2 points, then it must lie on the perpendicular bisector. So let's look again at quadrilateral ABDC. It was constructed by reflecting a figure. Remember, it was constructed by reflecting that triangle. That means that it has reflectional symmetry. Line segment BC is the line of symmetry of the figure. So let me go back and show that to you again. This segment right here, BC, this one running up and down, is a line of symmetry of that quadrilateral. It splits it into 2 perfectly congruent pieces. It's a line of symmetry. A line of symmetry can be an actual line in the figure, or it might be an imaginary line. A figure may have any number of lines of symmetry. Number 15, for each figure shown below, draw all the lines of symmetry. This triangle here has only one line of symmetry, and it would be a vertical line running just like that, make it a 90-degree angle. This rectangle has 2 lines of symmetry. We could split it vertically right down the middle, or we could split it horizontally right through the middle. This star has many lines of symmetry. We could split it here. Imagine folding it along this brown line and how the 2 halves would, line up perfectly on each other. We could split it here. This is a line of symmetry. Split it here. But we could even split it here. Again, imagine how this top section would fold over and line up perfectly there on the bottom section. We could split it across here, and we could split it right through there. And all these lines of symmetry, you're going to cross at that same dot exactly in the center of the figure. Number 16, triangle ABC has 3 lines of symmetry labeled L1, L2, and L3. What can you conclude about triangle ABC? Well, I think triangle ABC is an equilateral triangle. And here's why I know that. Because all of the sides are images of each other over the lines of reflection. Right? So this side right here is an image of this side, which is an image of this side over those various diagonal lines of reflection. And because they're images of each other, they will have to be the same length. And a triangle with 3 sides the same length is an equilateral triangle. Here's some check your understanding questions, so I will pause the video. So in this lesson, we worked with reflections. We did some reflections on a coordinate grid and also reflections without a coordinate plane. And we identified reflectional symmetry in figures by drawing their lines of symmetry.